computer. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, September 29, 2023. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a full moon evening in my hometown of Rockport, Massachusetts. If we could see it, it's overcast. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining ecosystems, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on Cape Ann's community access cable television channel hosted by 1623 Studios. I am grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation, comments, and general encouragement. This evening, I'm delighted to host Dr. Gerald Schieven, a former cohort of mine during our time together as astronomy graduate students at the University of Massachusetts in Amherst, Massachusetts. Gerald has since gone on to realize a rich astronomical career in Canada, so he's our first alien. After obtaining his PhD in astronomy at UMass, he worked at Queen's University in Kingston, Ontario, followed by NASA's Jet Propulsion Laboratory in Pasadena, California, Dominion Radio Astrophysical Observatory in Penticton, British Columbia, and the James Clerk Maxwell Telescope in Hawaii before moving to Victoria, British Columbia in 2008. For the past 30 years or so, he has been a staff astronomer at the National Research Council of Canada, otherwise known as the NRC, the Hertzberg Astronomy and Astrophysics Division, where he is responsible for managing Canada's support of the ALMA Observatory in Chile. This evening, Dr. Schieven will introduce us to the many wonders of the radio sky as revealed by the Atacama Large Millimeter Submillimeter Array, or ALMA. This stunning facility is situated in the high desert of Chile, where the clear, dry skies allow for unimpeded views at millimeter and submillimeter wavelengths. From baby stars to black holes, he will explain how ALMA can map myriad marvels of the cold universe that are invisible to our eyes. So, Gerald, thank you for joining us this evening. The Zoom platform is all yours now.
Well, thanks, Bill. Just commenting that it's been quite a few years since we've spent some time together. Yep. But I want to thank you very much for inviting me, because I love talking about ALMA and I love talking about astronomy. So I hope that you get a little bit out of my talk. First, I'm going to start sharing my screen. Oops, I better hold on a moment. And there we go. Now, can you tell me, please let me know, are you seeing my open screen that shows baby stars, black holes? And can you see my cursor rolling around the screen? Good, excellent.
Yes.
Good. So I'm going to start by insulting your intelligence. We are all interested in the stars. You look up in the sky and then on a good dark sky and a nice night, and you can see stars all over the place. But you might want to study fainter things. You may want to look at things much more detail. Excuse me, I'm giving a talk. Thank you. Great time for the custodian to show up. So stars, you want to look at stars. So you would pull out your trusty telescope. Like this big white dome is the dome from the Dominion Astrophysical Observatory here on a mountain in Victoria, British Columbia, where I'm now working. Here's a telescope, a Lowell Observatory in Arizona. Here I am watching an eclipse in with my trusty little Celestron 6-inch. Or you might use a much bigger telescope located on a mountaintop, like here in Hawaii, the Mauna Kea Observatory. So you have used an optical telescope if you want to study the stars. But if you look up at the stars, particularly if you look up toward the Milky Way, you can see all these dark areas, these dark patches going all the way up. And those places don't seem to have very many stars at all. But that's not because there are no stars in that direction. It's because there's huge clouds of gas and dust that are obscuring the stars behind them. But there's all this stuff out there. We want to be able to study them. How do you study stuff that is invisible? Well, for that, I want to look a little bit at why things give off light. And so let's do a little experiment. Let's be old-fashioned and think about an electric stove that has the old-fashioned elements. I know everybody's into induction coils and things like that for stoves these days, but the old-fashioned electric stove still had an element on the top of it. You turn the electricity on, and after a minute or so, the stovetop starts to glow. It's giving off visible light. Why? Because it's very hot. Things that are very hot, like stars, like the sun, give off visible light. And this is the visible light that you can see with your eyes. So your eyes are good detectors of visible light. Of course, if you want to detect really faint things that give off only a little bit of light, you'd use a telescope. Telescope is just a big light bucket, gathers a lot of light that is covering a much bigger area, so you can get much more power and feed that through your eyes, so you can see much fainter things. But great. Well, let's go further a little bit. Suppose you turn the element off on the top of your stove. It's still pretty hot. Don't put your hand on it. But it's still giving off forms of electromagnetic radiation. It's still giving off infrared, and you can detect infrared with your hands. I mean, go outside. If I went outside now, it's a nice sunny day, so I hold my hands up toward the sun. I can feel the infrared light coming from the sun using my hands. It's not a very sensitive detector. My hands are not very sensitive. You want to detect the infrared light from warm things, then you'd need to have a special telescope. So just to reiterate, hot things give off visible light. Turn off the stove, it's not so hot anymore, but it's still pretty warm. But it's giving off lots of infrared light. Well, that's really great. You want to study things that are warm but not cold in space, then you would use a telescope that's sensitive to infrared light, like the James Webb telescope that you've been seeing so many amazingly beautiful pictures from lately. You can build an infrared telescope on Earth, but you have to build them up on mountaintops where it's nice and dry. Well, let's take that element from the stovetop, and now let's throw it into a vat full of liquid nitrogen. Now it's cold. It's really cold. It's so cold that there's no visible light coming from it. There's no visible light at all coming out from something that cold. And there's very little infrared coming off of it as well, but it's still giving off electromagnetic radiation. It's giving off microwaves. Now I'm going to be interchanging what I call microwaves from time to time, and mostly microwaves, we usually talk about them in terms of the wavelength of the light. The infrared light that comes out in microwaves. The microwaves have wavelengths of a few millimeters down to down to tenths of a millimeter, or even smaller. And so I might be talking about millimeter wave microwaves or submillimeter wave microwaves. You can really think of them as very far infrared, because we're looking at very cold stuff, like a few tens of degrees above absolute zero. Well, if you want to study that stuff that is really cold out there, then you need to have a telescope that is very sensitive to microwaves, to millimeter and submillimeter wavelengths. So you build a kind of a radio telescope like this one that used to be in central, just north of Amherst, Massachusetts. This is the Five College Radio Astronomy Observatory, FCRAO. This is where Bill and I both got our PhDs, and in fact, I was just confirmed. This, in fact, is Bill, right down here, in front of the telescope. The telescope is built inside of a radome to protect it, because the radome is transparent to millimeter waves. Then you can keep it nice and dry and safe. So the telescope itself looks like this. It looks like a big satellite dish. This telescope is really sensitive to millimeter waves, but the bulk of the radiation that comes from these really, really cold objects is peaks in the submillimeter waves. Now, the problem with submillimeter is that it is very, very sensitive to the amount of water that is in the air. I mean, to think about it, how a microwave oven works. You put stuff in your microwave oven, shut the door, turn the microwave oven on, and it starts beaming microwaves into your food that's in your microwave. And what the microwaves do the microwaves are absorbed by the water. Makes the water molecules start to rotate and spin, and then they start jostling against each other, and it heats the water and the food inside your microwave oven. Well, the same thing is happening with the water in the air. The water in the air absorbs the microwaves coming through the atmosphere, and it prevents the microwaves from getting to the ground. So in order to detect them, you have to build a telescope that is so high up that almost all the water vapor in the atmosphere is below you. For instance, in Mauna Kea in Hawaii. And that's where this telescope is built. This is the James Clerk Maxwell telescope. I worked here for about 13 years until about 2008 when I moved here. It's built, again, it looks like a giant satellite antenna inside of a dome. And it's also built on top of Mauna Kea at an elevation of about 4,000 meters above sea level, and where it is extremely dry. Now, these are all optical and infrared telescopes, but down here, this is Submillimeter Valley. There's the James Clerk Maxwell telescope right there, and then a couple of other submillimeter observatories over here. And yes, of course, there's yours truly in a control room of the JCMT when we were actually trying to detect do you remember about 15 years ago, the Deep Impact mission? They sent a big bullet crashing into a comet to try and break the comet and make a big cloud of dust coming from it. And this was us trying to detect it in the submillimeter. We never did, but it was fun trying. Well, that's fine. We've got a telescope. It's now capable of looking at really cold stuff out there, of which there is a heck of a lot. All of those dark clouds that we saw in that picture in the beginning, those are all made out of very cold dust and molecular gas. So fine, what do we use this telescope for? Well, we use the telescope to study all of this gas and dust between the stars, like where the material is. We want to map where it's located in the galaxy, how much there is, what's the density, what is it made out of, how is it moving, how cold it is, what the temperature, all the physics, all the physical properties that you can detect. Oh, and chemistry as well. Here's a very, it's a list, a very incomplete list of some of the very smelly molecules that have been detected in the interstellar medium. But studying chemistry also tells us something about the history of these of the gas clouds and how old they are, kinds of things that are happening in them. We learn the motions of these clouds, how they are, how they're moving, how stars and planets are forming, and how the universe forms, in fact. Well, one thing that you can do is to study the atmospheres of planets. And this is a project that I was involved in when I was working at the JCMT, where we were observing the upper atmosphere of Mars, trying to measure the temperature and density profile of the upper atmosphere of Mars. And this was more than just because, hey, it's there, we wanted to learn about it. One of the NASA probes that NASA was sending to Mars, they wanted to save fuel, but they wanted to put it into orbit around Mars, of course. But in order to save fuel, they decided that they were going to try doing aerobraking. In other words, using the Martian atmosphere to try and slow the probe down to put it into orbit around Mars. But to do that, you need to know very precisely how thick the atmosphere is, how hot the atmosphere is, and how deep it is, so that you can aim the spacecraft at just the right place so it doesn't burn up and it doesn't just keep going beyond. So this study was trying to study helping out the NASA to get this thing in orbit. But in the process, we made a discovery of hydrogen peroxide. This is an absorption line of hydrogen peroxide in the atmosphere of Mars. We were the first ones to detect it. And when they were writing up the paper to publish, I suggested that they title it that Blondes discovered on Mars, but for some reason they didn't go for that title, but who knows why. Well, let's look at another region which is very familiar. I'm sure you all recognize what this is. Does anybody not recognize what we're looking at here? I'm sure you are. Here's the hint. There's the 3 stars in a row forming the belt. There's the shoulder of the giant, Betelgeuse. Down here is the knee, Rigel. This is the constellation Orion. Taken with a very, very, very long exposure of, I think it's just an ordinary SLR digital camera, but a very long exposure and revealing all kinds of stuff. You see all these little black splotches, dark lanes going across here. This big red circle, this big red circle is hydrogen gas that has been heated up by stars inside this region, probably these stars and the stars in here. But and right here, you might recognize this little dot right here. That's the Horsehead Nebula. But we are here seeing the stars, and we're also seeing very hot gas. But I want to look down here at these stars down here. This is the belt of Orion. But let's just look. I want to look a little bit more closely at it. Here's another photograph of an optical photograph of the Orion Nebula. There are 4 stars here, that 4 O-type stars right here that are very, very hot, very, very young as well. they're so hot that they're heating up the gas around it, causing it to be ionized and to glow like this. This is the Great Nebula in Orion. It's a big H2 region, it's called. But you can see all these filaments, these dark lines. And we see a few stars, but only the ones that are in front between us and the cloud here. If you use an infrared telescope, then you can look deeper into the cloud, and you can start to see thousands and thousands of very young stars, less than a million years old, that are all in the process of being born. Around them, there may be planets forming. But even here, we are still not seeing, we're seeing some of the gas, but only the warm gas. But if we want to study the cold gas, the reservoirs out of which these stars are forming, we can use the millimeter and submillimeter waves. And that's what this is. We're looking now at the gas and dust itself. It forms this big, long filament. Here's the Orion Nebula right in here. It's heating it up. That's why it glows more brightly. But there's all these filaments, and in these the brightest parts in here, if we study them in detail, you can find new stars being formed that you can't even see in that previous picture yet. We can also study nearby stars. This is an image taken with the JCMT of Epsilon Eridani, which is a nearby star. It's about it's less than 10 light years away. It's a star which is about 600 million years old or so, but you can't see the star itself in this picture. It would be right in this area. But this is a disk of dust around the planet with this big hole in the middle. What you're looking at here is something called a debris disk. It's let's just take this is an artist's rendition of what that is. Epsilon Eridani is now known to have several planets within that hole that you saw in the image, and surrounding it is a debris disk. It's a disk of dust that has been created by comets colliding with each other. Now, it'd be interesting to see it would be interesting to be on a planet circling inside this region. On Earth, we see comets. You know, you've seen a bunch of comets, the lovely comets in the last couple of decades. But imagine if there were thousands of comets every year. That's about the number of comets that there are falling into this solar system at any one time, and the comets are colliding and they're breaking up and causing this debris disk around the planet. And it was first discovered with the James Clerk Maxwell telescope. And one more thing we've been using to study the universe. This is an optical picture of the Hubble ultra deep field, and you see every single one of the points you see in this image is another galaxy. We are definitely not seeing all the galaxies in this direction. If you look in the submillimeter, you can see all these points, these bright spots here. I have to admit, this is one of the most boring images I have ever seen. However, the consequences of this boring image are really important, because this is a whole class of galaxies that was not known of at all, and they do not have any optical light. You do not see them in the optical. They may be visible in the infrared. But what's happening in them is that there is so much star formation going on in these galaxies. These are in the early stages of forming the vast bulk of the stars in their galaxies. And so these are they're so-called sub-millimeter galaxies. They used to be called scuba galaxies after the instrument from the JCMT. Well, that's fine. We've got this nice big telescope, the JCMT, that I was working for many years. We've made all kinds of discoveries. We have added so much to our knowledge about how stars form and how this interstellar medium works. Why do we need a bigger or better telescope? Well, the answer to that is sensitivity and resolution. Obviously, if you have a telescope of a certain size, you're catching light that falls on that telescope and lets you see to a certain sensitivity. You can see faint things. If you make the telescope bigger, you can see much fainter things. But you'll also have the improvement in the resolution. The resolution is just how fine a detail can you see on a picture. Like, for instance, if you just go outside at night and have a look at the moon, you can see all kinds of features on the moon. You can see these bright patches and dark patches and so on. But and there are a couple of craters that you can actually see with the naked eye. But if you want to study craters in detail, you need a much bigger telescope to see fainter things and things in much better detail. So we need to make bigger telescopes to see things in finer detail. Oh, for example, let's say we're looking at something. We're not sure what this is, but we have a small telescope here looking at the sky. Because we don't have much resolution, we're seeing a lot of blobs. You might be able to use a spectroscope to tell what these are made of, but you don't necessarily know what they are or what they're doing. If you make your telescope much bigger, then you can see things in finer detail. You can now see that, oh, there's some structure in here. There are bright areas, there are faint areas, there are bigger areas, there are small areas, but we're still not seeing much detail in this picture. But if we make the telescope really big, then you can start seeing that, oh, we're looking at the flowers. And we can start making out details of petals and see veins in the leaves. But what happens if, for example, we wanted to say, oh, what is this spot? It's just a spot. Is it a bug? Is it a hole in the leaf? In order to study that, we would need to have a much bigger telescope yet. But building enormous telescopes is pretty well impossible. I mean, the James Clerk Maxwell telescope can see things of the order of about 15 arc seconds. That's the resolution. But if you wanted to study, say, the formation of something the size of our solar system at the distance of the closest star-forming areas, you would need to see things about 1,000 times finer resolution than you can possibly do with the JCMT. Well, the JCMT is 15 meters in diameter. If you want to study how planets form in nearby star-forming regions, you would need a telescope that is about 1,000 times bigger. You'd need a telescope 15 kilometers in diameter. Well, I'd like to know how you're going to build a telescope that big. You can't do it. And then even if you did manage to make one giant dish that big, you can't steer it. There's no way you're going to be able to steer the thing and move it around the sky to look at different things. But fortunately, there's a trick. We don't have to have one telescope that huge. You can have instead little pieces of it. In other words, small antennas, but that are scattered all over the place. And that's the reason why interferometers were developed. Instead of having one giant telescope, you can have small telescopes, but lots and lots and lots of pieces of them. And that's where the Atacama Large Millimeter Submillimeter Array, ALMA, comes in. Here we have 66 antennas, each the size of the JCMT, not quite, but almost the same size, 12 meter in diameter dishes instead of 15. But we've got 66 of them instead of just one. And because they are lots of antennas, you can pick them up and move them. So you can have them close together as about 200 meters. So a telescope 200 meters in diameter, or you can move them outward to make a telescope 16 kilometers in diameter. Well, needless to say, building a telescope that big and with that many antennas is very, very expensive. And so one country can't do it. ALMA is, in fact, a consortium of a lot of countries in North America, including US, Canada, and for some reason, Taiwan. Europe, which are mostly the European Southern Observatory, and also East Asia, including Japan, Taiwan, and now Korea. Yeah, I know Taiwan is in both North America and East Asia. I'm not sure how that works. It is built in northern Chile on a very high site, about 5,000 meters elevation. The JCMT in Hawaii is 4,000 meters, so this is another kilometer higher. And there are 66 telescopes all working together like one giant telescope, anywhere from 200 meter diameter to 16 kilometers. It's located on a very large flat plain at a very high elevation in northern Chile. This is the control room, the control building right here. But here you can see the 66 antennas in the compact configuration, where the maximum size is about 200 meters. But you can also have the antennas scattered over a vast plain up to 16 kilometers apart. Well, to do that, you have to be able to move them. And so there's this specially designed truck, actually two of them, that can back up to an antenna, literally pick the whole antenna up, and then drive it around to wherever they need to move it to, and they can also drive it down to the mid-level facility where they can do repairs if necessary. I have had the opportunity of being up at the summit only once, and that was quite a few years ago. I go back to Chile and I go back up to the ALMA Observatory 2 or 3 times a year, but they're very careful about who they let up to the high site. And alas, my blood pressure is no longer quite good enough to let me go up to the top where all the antennas are. So I'm hoping that this time when I go back, I'll be back again in a month. In fact, I'm going to try once again, see if I can go up to see the telescopes up at the high site. But the high site at 5,000 meters, it is very high. It is very difficult to work up there. So most of the work, the observing, the repairs, the assembly, and so on, are done at the mid-level facility. That's at about 3,000 meters elevation. So this area is where they put all the antennas together before they drove them to the top. This is the control center. These are residences over here, and here's a closer look at the control building is here. Anytime because there are so many countries that are involved in the telescope, every time there are dignitaries coming, they put all the flags up. Looks very impressive. As soon as the dignitaries leave, they take them all down again. So I was just lucky enough that they had the flags up for this picture. And here it is in the control room. It's a lot. You'll notice it's a lot bigger than at the JCMT. A lot more room, also a lot more people. But there are not just people and not just astronomers up at the high site. There are also the local residents, wild burros. And I took all these pictures, by the way. These are all mine. The Andean condor, Chilean foxes. These are vicuña. It's a wild llamas, flamingos. And this cute little guy, this is not a rabbit. This is called a vizcacha. It's actually it's a relative of the chinchilla. And it hops like a rabbit. It's got rabbit ears, but you notice the tail. It's a nice, it looks more like a pigtail. Well, there's a family of vizcachas that lives right near the observatory. And when I go visit, I like to go hiking out on the grounds and go visit the family. Other things that are in Chile, they're probably in the high desert where ALMA is located. It is one of the driest places on Earth. There are spots not far from the observatory where they get rain maybe once every 10 years or so. There's more rain up at the high elevations, but that's mostly because of occasional fog. Here's a salt lake up in the high desert. It's exquisitely beautiful up there. There are also these salt mountains, and here you're looking out across the Atacama Plain. This is the Valle de la Luna. These are salt hills. If you look way up here, you see a little white patch. That's the mid-level facility, about 40 kilometers away. And because it's a very seismically active area, it's also volcanically active. There are geysers not far away. And there are volcanoes. And here's a picture of the Lascar volcano, which erupts every few years, taken from near one of the residences up at the mid-level facility. And there are contingency plans in case there's a major eruption. And of course, the landscape is just absolutely astonishing. It's and they probably won't let me go exploring these areas anymore. Apparently, up at one of the neighboring observatories, one of the British astronomers went for a walk and never came back. I think it was 2 or 3 months before they found him, fallen into a crevice like this. And cacti. Most of the cacti are at higher elevations, but this is a lonely cactus. And you can see the mid-level support facility in the background. But of course, the main reason that you go to, that ALMA is built where it is because it is extremely dry, very little water vapor. And so the skies are very clear in the millimeter and submillimeter. Well, let's have a look at some of the interesting things that have been coming out. If you go to almaobservatory.org, you can check out their press releases. There are new ones coming out all the time. And so just amazing pictures that are coming out of this. One of the first discoveries was a game changer in the study of how stars and how planets form. These are images of very young stars. Let's probably have a quick explanation of what's going on. We start off with a giant cloud of gas. It becomes gravitationally unstable, and then it starts to shrink. And as it shrinks, if it had any type of rotation at all, think of a figure skater that is spinning with their arms outstretched. As they pull their arms in, they spin faster and faster and faster, faster, faster. As this gas cloud shrinks, material falls in toward the center, and as it spins, it starts spinning faster and faster. Eventually, it has a hard time fully moving this way. If it's rotating like this, it doesn't like to move this way, but it does fall this way. So it tends to fall into a pancake shape. So here we are looking at this pancake. It's a disk around this newly formed star in the center. Well, what was astonishing to see were all these dark lanes. These are caused by planets forming inside this disk, and they are sweeping out these gaps in the disk. Here's another one where you see these gaps in the disk, and there are planets forming inside these gaps. What was most astonishing was that this was happening very early, much earlier in the star formation process than anyone ever expected. So these images have really been game changers in our understanding of how planets form. And it's not just a few examples. Oh, this is just an artist rendition of what this might look like. In the middle is the star that's formed. It's heating up the gas around it, forming a little gap here. But then you get this disk of material, planetesimals forming. Planetesimals get larger. They start sweeping up dust inside these rings, forming all these empty rings inside this cloud. And of course, that's why planets tend to be in a plane. They form in these flat disks. Here's a bunch of these circumstellar disks around newly formed stars, and you can see these rings and spiral patterns are all pretty well ubiquitous. Very few of them are just smooth. So planets form really early. We also have been using ALMA to study galaxies. Because we have such high resolution and such sensitivity, we can study the molecular gas and the star-forming regions in other galaxies to the same with the same level of detail that we can in our own galaxy. And so now, instead of having just one galaxy or one type of example of a star forming, we now have hundreds of thousands of star forming regions. You can start doing statistics and start understanding the physics of how these stars are forming and how planets are forming. The one thing I wanted to show you was what was a really exciting result. Maybe in about 3-4 years ago, the first result was released of an image of a black hole. Now, this is a cluster of galaxies. This is an optical image of a giant cluster of galaxies in Virgo, but I want to focus in on this one right here. It's the biggest galaxy in this cluster. Looking a little bit closer, you see the galaxy is a big fuzzy blob, basically. It's an elliptical galaxy, but in the middle of the galaxy, there is this something. Looking closer, you can see that this is a jet coming out from the center of the galaxy. Something is shooting this jet out for tens, hundreds, thousands of light years. So something very energetic is taking place in the middle of this galaxy. Well, using optical telescopes, you can see that as you get closer to the center of this galaxy, the stars are moving faster and faster, faster. Something in here is very, very heavy. But there are so many stars in the intervening material, and if you start looking very close to the center, you can't see into it because of the gas and the dust in the optical. Even the infrared is completely opaque. when you start looking close enough into the center of this area. But you can probe it with millimeter and submillimeter waves. And the theory was that there was a giant black hole in the center of this galaxy. And in fact, we believe that there are giant black holes in the center of all galaxies, but this is a particularly big one. It was realized that if you could build a telescope about 1,000 times bigger than ALMA, that you could actually image the black hole at the center of M87, that's the name of this galaxy, and also the black hole at the center of our own galaxy. And so the idea of the Event Horizon Telescope was made. ALMA is about 16 kilometers in diameter, but they needed one that was about 16,000 kilometers in diameter. And the only way to do that is to have telescopes scattered all over the Earth. So there is a network of millimeter and submillimeter telescopes scattered around the Earth, including ALMA, Apex, which is another one here down in Chile. The South Pole, there is a submillimeter telescope there. There's one in Mexico that was a big project from University of Massachusetts that finally is working. There's one in Arizona, a couple in Arizona. There's the JCMT in Hawaii. There's one in Greenland. There's one in Spain, and there's one in France. And these telescopes are working together in the Event Horizon Telescope to be able to get enough angular resolution to be able to image the black hole at the center of M87. So this is just an artist rendition. It's actually not a very good one because it doesn't really take into account the really relativistic effects. But the idea was that what they wanted to see this region down here. So they designed the telescope. It took many years to get the telescope, all of the telescopes working together. I happened to be the astronomer on duty during one of the Event Horizon Telescope runs. And it sounds like it would be really exciting to be there at the time because, hey, they're imaging the black hole at the center of our galaxy. And I thought, oh, that should sound really exciting to be there, except that whenever the weather was good, the Event Horizon Telescope team would come to the control room and say, okay, we're taking over the telescope. You go over and sit in the corner. Don't go away because if the weather stops being good, you're going to get the telescope back. So I couldn't leave, but had nothing to do. It was one of the most boring observing runs that I've had. It was cool knowing what was going on, but it was just not very exciting. But anyway, the models show that this is what it should have looked like. And of course, you've undoubtedly seen this image and all of the memes that are attached to it. What we are seeing here is this dark hole is actually the shadow of the black hole. It's not the black hole itself, but it is the shadow of the black hole. Around it, you see all this glowing emission. This is not just stuff in a donut around the black hole. This is mostly the stuff behind the black hole on the other side from us. But the black hole is bending the light so that the light that would be coming out from the stuff behind the black hole is actually being bent toward us. Now the black hole is rotating, and the material that is close to the black hole is also rotating around the black hole, and so you get some relativistic effects that make the one edge brighter and one edge fainter. Just to give you an idea of how big this thing is, the black hole in the center of this galaxy is about 6.5 billion times the mass of the sun. and the size scale that we're looking at, this is the orbit of Pluto compared to the shadow of the black hole. At the time of this picture, Voyager 1 was this far away from the sun, right about the edge of this the bright edge, the bright disk. So this thing is large, but remember, this thing is also 54 million light years away. So this image is the resolution here is of the order of microseconds, micro arcseconds. It is really very high resolution. More recently, they released this image. This is showing the orientation of the magnetic field around the black hole, and it's this beautiful, incredible spiral. I don't understand the physics of how you get a magnetic field that looks like this, but it's quite an impressive image. About a year ago or so, they released an image of the black hole on the center of our galaxy, but it looks a lot like this. So I haven't shown that to you. Well, at some point they will want to look at things in even finer detail. So apparently the Event Horizon Telescope team is now in the process of applying for funds and doing studies to see if they can put satellites in orbit, in very distant orbits around the Earth, to now get telescopes that are several times further apart, to look at even finer detail of this black hole, and to see to image black holes around other galaxy centers. Well, that's only a very tiny flavor of things that have been discovered with ALMA. Definitely go to this website, almaobservatory.org. Look there, you can find lots of pictures or lots of images, and they also have a list of all the press releases that have ever come out from ALMA. ALMA just had its 10th anniversary of first light, and it is only just beginning the discovery of the universe. So I hope you got a little bit out of this. I think I'm going to stop sharing at this point, and I hope I haven't run over time.
Fabulous. You're good.
Ooh, just got there.
We have time for questions. Why don't I get it so that it's in the gallery? There we go. There we go. Okay. I'm sure there's some questions. Feel free to unmute.
First of all, thanks. It's very good. I enjoyed the presentation.
Oh, thank you.
Like you had a lot of fun doing things.
Oh, yeah.
When you were talking about the, I don't know, looking at the black hole in the center, wasn't our galaxy you saw it in, somebody else's, right?
That's right.
M87.
That's right. This is the galaxy M87. M87 is about 1,000 times further away than the center of our galaxy.
Sure, but it's easier to get at.
But it is also 1,000 times bigger than the one in the center of our galaxy.
Right.
So by extraordinary coincidence, they both have about the same angular size. Unfortunately, the black holes in the event horizons of black holes in other galaxies are all smaller. So these are really the only two that we are going to get images of using the Event Horizon Telescope as it is now. So that's why they're talking about adding satellites in orbit to get bigger baselines in order to be able to image other black holes.
An incredible image.
No kidding. It was pretty exciting.
I went to a star party here in locally, and I actually saw that jetted optical jet that you showed in a guy had a sharp cap program that we put a lot of images together, and it was very small, but you could see the galaxy and the jet going away from it. It was like,
oh,
wow.
Nice.
Incredible.
Yeah. I have to say that the images that are coming out of amateur astronomer telescopes now far outstrip the anything that was ever produced by a professional telescope, by a big telescope, even when I was a grad student. They are absolutely stunning. And this is with moderate sized telescopes. It's just the camera equipment and technology is just so good.
I just bought that solar filter for my Celestron 6-inch. And I'm looking forward to going to New York State next April and trying to get into the actual umbria of the eclipse by driving towards Niagara Falls a couple of hours from my friend's house in upstate New York. And if I can just get into that arc, I could actually be in the totality of the eclipse.
Oh, it is so amazing. It is just so. I had my first total eclipse just for the last one in 2017.
Wow!
And it was a spiritual experience. It was.
I didn't go to the total, but we saw part of it here.
Yeah. The difference between 99.5% and 100% is mind-boggling.
Wow!
So you have to go to totality. Yeah, me too. And I hope you have clear skies.
Yeah.
So we have some people with raised hands. Why don't we start with Marie?
Oh, okay. I was just curious. You were talking about the telescope and wanting more detail, so it would have to be like the size of continent.
Yeah.
But I was wondering if that can be imitated in a different way. Are they working on like I don't understand the actual effect or the quality that would create that much light into it. Is there another way do you think they're going to be working on another way to create that quality, but in a more realistic?
Well, there are two things that you can do. One is build the telescope bigger and bigger and bigger. And the other is to look at shorter and shorter and shorter wavelengths. So the resolution that you get is a function of the wavelength of light divided by the diameter of your telescope. So you can either make your telescope bigger or you can make your wavelength smaller. Now, the problem with making the wavelength smaller is that when you get to for instance, you could look at it in the infrared. That's a much shorter wavelength, and so you could get 10 to 100 times better resolution with a telescope the same size. The problem is that when you get into the infrared, it is now optically thick, and you can't see down to the black hole. So you have to choose it. So it's a trade-off between being able to see down into the thing that you want to look at, and building it big enough to be able to do that.
I see.
That's
it's
why
going to take a while.
It's going to take a while, yeah, and it's going to cost a lot.
Tony.
Hey, Gerald, thank you so much for the talk. It was fascinating. So I'm a former student of Bill's at Tufts, and I'm now finishing my PhD at Wyoming here. I'm in my office. And it very much caught my attention because you had a photo of from ALMA of NGC 4254 or M99. And I actually literally, I just today submitted my AAS proposal to study for my abstract to study the bubbles and the voids within that galaxy for the January meeting. So I was wondering if you could actually show that frame again, because I saw two beautiful voids within that galaxy, and I haven't actually seen the ALMA imagery from that yet.
Okay.
Let me share the screen of galaxies.
Yeah. This one.
So that is ALMA, or is that infrared there?
This is ALMA.
Okay, that's beautiful.
All of these data are available from the archive. They're all public domain now. You can just download them from the ALMA archive, or you can go to the FANGS website.
Oh, so this is FANGS. That's the group that I'm working with.
Oh, okay. So you've got the data already. Yeah.
So yeah, is it the CO maps then? Is that what this is looking at, or?
Yes, these are the CO maps.
Okay, great. I was just pulling that up on my other computer here to see if we have that, and I can't find it. So that's beautiful. Thank you so much.
Okay. Cool. Yeah, these are incredible. These images. Yeah. I saw them and my jaw just dropped. Yeah. Almost as much as when my jaw dropped when I saw that image of HL Tau.
Same thing with the web images that were. So we have our the next 19 galaxies of the FANGS group we're getting as well for in cycle 2. So those should be coming out here very shortly. So excited to see those too.
Yeah. Good stuff.
Yeah, thanks again.
Yep. Okay.
I have a more practical, pragmatic question. As you said, being up at 16,000 feet is tough health-wise.
Yeah.
And I certainly appreciated that going up to Mauna Kea at 14,000 feet and visiting, I think it was the sub-millimeter telescope. I don't know if it was JCMT. Isn't there another one?
There's the JCMT, there's the sub-millimeter array, the Harvard-Smithsonian sub-millimeter array, which is a small version of ALMA. There's also the Caltech sub-millimeter observatory, which is now closed. That's the one that I went to. The one that looks like a big football helmet.
Yeah. Well, I everything was okay. We had acclimated in the midway spot for several hours with lunch and stuff. But then I climbed 2 stairs to enter the building, and I had to lean against the doorway. And I was, a decade or 2 younger than I am now, so I can really appreciate the problems. What about using oxygen?
Some Diamox before you go to altitude.
Yeah. That building that I said was the control center at altitude. Actually, people don't actually work in there, but it is they do have a higher oxygen content in the air, and they also they didn't force you before, but apparently now they do require you to wear an oxygen mask when they're working at altitude.
Take Diamox before you go to
3,000. 3,000 meters. They don't bother.
So Mario, you're suggesting that you take some sort of medicine?
Yeah, it's an FDA-approved medication to help prevent altitude sickness. 500 milligrams BID twice a day. You start 3 or 4 days before you go to altitude, and you have to drink a lot of water. It used to be a blood pressure pill. It's not used for that anymore. It's only used as high altitude sickness. So the way it works is it causes you to lose, it acidifies your blood because it makes you lose alkaline in your urine. So it makes you pee. But by acidifying your blood, even when you're sleeping, your brain says your blood's too acidic, so you got to breathe more. So it forces you to take more deeper breaths. And by doing that, you take in more oxygen. It actually works.
And where it depends.
Where it depends. Well, that I only work between the neck and the diaphragm. Okay, that's someone else's problem.
All right.
Yeah,
that's an established and acceptable use for Diamox. You can look it up.
Maybe I should ask my doctor if I can bring some with me the next time I go down.
Yeah. Well, I did a great experiment when we went to the Bolivian eclipse in 1994. We had about 100 people, and half of them took Diamox and half didn't. The ones that did pretty well, and the ones that didn't were sick for days. That's when I became a believer.
Yeah.
Well, we certainly, when I worked for the JCMT, and we actually observed at 4,000 meters routinely, as a support astronomer, I had to give everybody the safety briefing, and the telescope operators were very careful about making sure that the observers were not suffering having altitude sickness. And I have had to take people down to sea level before, and I had somebody collapse on me. I mean, collapse on me. So,
oh my goodness.
Yeah, if you go into full-blown crisis, you have to get more pressure.
Yeah,
Diamox won't help at that point.
Yeah.
So long, Tony. I just wanted to ask about the use of ALMA for detecting complex chemistries.
Yeah.
Is it used for much of that, or is that pretty much more of a green bank telescope affair?
No, there are plenty of well, there are a lot of molecules that you can get with ALMA that you can't get with green bank. Certainly green bank has a real niche in that, but ALMA also does. And actually, one of the things that I did recently was just commission a spectral scan mode that lets you do spectral scans even with the total power array. I won't go into detail of what that means, but we have a fairly wide bandwidth, but you still have to do a lot of tuning to do a complete spectral scan, and so this was involved in being able to do that easily.
That sounds interesting.
Yeah. Perhaps you'll help break the confusion about phosphine in Venus.
I'm actually involved in that project with Venus, the JCMT Venus project, and I'm not specifically on any ALMA proposals. I think they're trying to get more data from JCMT first. But yeah, that's I'm the Canadian coordinator for that.
Any of you guys know if Arecibo is ever going to get rebuilt?
I do not know.
Yeah,
I rather doubt it.
That's too bad.
Yeah, they don't. Arecibo doesn't have a Senator Byrd.
Exactly. Well, right now, ALMA is the premier telescope anywhere at these wavelengths. Isn't that correct?
Oh yeah, by several orders of magnitude.
And it wasn't cheap.
Oh no, it was about $1.5 billion to build, and I don't know what the annual cost for operations, but it's in the tens of millions.
Yeah, it's fabulous.
So Canada contributes both money and in-kind support, and that's mainly what I'm doing these days. I used to do a lot more research, but I've been finding that the ALMA support has been a lot more fun. And I figure for my group, we're responsible for taking care of ALMA, and I figured that the other people in my group are all real hotshot researchers, and I figured my contribution to research is better doing all of the support stuff and giving them more time to do their good science.
Well, I'm very happy to learn that you're manning the helm or staffing the helm, and it sounds like the observatory is in very good hands. And so with that, I think I'm going to close this out and wish all of you a great evening, and a special thanks to Gerald, our first Canadian.
Thank you very much.
My pleasure, and thanks a lot.
Okay. Have a great night.
Great. Bye.
Bye.
Good night. Bye-bye.
Bye.
Yeah.